Hi, my name is Hazel Beeman. I'm a freshman philosophy and economics major from Seattle, Washington, and today we're going to be talking about Alan Turing and John Searle. So, imagine you're sitting across from your computer and asking it questions through the screen. If its responses are so convincing that you can't tell whether it's a person or machine, would you say that it's intelligent? This is the scenario Alan Turing proposed in what he called the imitation game. For Turing, the key question isn't can machines think, but rather can a machine imitate human responses so well that we can't tell the difference? If it can, Turing argues that we should treat it as intelligent. Turing's approach is behavior based. He shifts the focus away from the inner workings of the mind and towards observable output. In other words, it doesn't matter how a machine works, but what it does, or the output that it produces. If its behavior is indistinguishable from that of a human, then it deserves to be included in the conversation about thinking beings. But not everyone agrees with that standard. Philosopher John Searle presents a powerful counterargument through his famous Chinese room thought experiment. Imagine a person inside a room manipulating Chinese symbols according to a rulebook. To an outsider, it might seem like the person understands Chinese, but really they're just following instructions. Searle uses this to show that simulating understanding is not the same as actually understanding. For Searle, the heart of the matter is intentionality, the capacity of the mind to be about things, to hold meaning. He argues that a computer, no matter how convincing its responses, is only manipulating symbols. It has no grasp of what those symbols mean. In other words, syntax alone, rules for moving symbols, can't produce semantics, actual meaning. So, while a machine might pass the imitation game, it still would not have a mind. Ultimately, Turing and Searle disagree on what it means for a machine to think. Turing says if it walks like a duck and quacks like a duck, we call it a duck. Searle says, sure it quacks, but that doesn't mean there's a duck inside. One view emphasizes performance, the other emphasizes internal understanding. And between them lies one of the most important philosophical questions of our time. Is intelligent behavior enough to count as a mind, or is there something more going on beneath the surface? Our group will choose the side of John Searle, which we'll talk about in the conclusion. But yeah, thank you.
Whose work laid the foundation for modern computer science and artificial intelligence. In this passage, Alan Turing introduces his famous idea of the imitation game as a replacement for the vague question, can machines think? He argues that trying to define machine and think based on common usage is unproductive and can lead to absurd methods like public opinion polls. Instead, he proposes a new idea, a game involving three players, a man A, a woman B, and an interrogator C, where the interrogator must determine which of the two hidden participants is the man or the woman, based solely on written responses. The man tries to deceive the interrogator while the woman tries to help. Turing then suggests modifying the game by replacing the man with a machine, and asks whether the machine can fool the interrogator as often as a human can. This forms step one of the imitation game, reframing the philosophical question of the machine intelligence into a practical experiment that tests whether a machine can convincingly imitate human responses. Turing then reframes the vague question, can machines think, into a clear one. Can machines successfully play the imitation game? This test focuses on observable behavior, intellectual performance via written communication, eliminating biases like appearance or voice. Turing supports the test fairness with examples involving poetry, math, and chess, showing it measures intelligence without relying on irrelevant traits like beauty or strength. He acknowledges that machines may think differently from humans, but argues that success in the imitation game makes such objections irrelevant. Next, Turing defines the kind of machines to consider, narrowing the focus to digital computers, particularly electronic ones. Due to their versatility and scientific relevance, he excludes biological methods like cloning, arguing that intelligence lies in computational ability, not biological form. Importantly, Turing isn't evaluating current machines, but whether any digital computer could, in principle, succeed. This step answers the question of machine intelligence in a clear, practical, and scientifically meaningful context. Turing continues his argument by explaining digital computers, marking step 4. He compares them to human computers who follow rules and breaks them into three parts: the store, memory, the executive unit performs operations, and the control manages instruction order. These elements computers to carry out complex tasks, including loops and conditional actions. Programming, he explains, is simply translating human problem-solving methods into machine-readable instructions. Turing also explores variations like computer with random elements and theoretical machines with infinite memory. He emphasizes that intelligence depends on structure and function, not the medium, highlighting that even a mechanical machine like Babbage's analytical engine could, in theory, stimulate intelligence. In step 5, Turing introduces discrete state machines, which move between finite states and model digital computers accurately. He argues that digital computers are universal machines capable of mimicking any discrete state machine if properly programmed. This means one computer can, in theory, do the work of any other. As a result, the key question becomes whether a well-designed digital computer can play the imitation game convincingly, reinforcing that machine intelligence is not only possible but achievable through computation. In step 6, Turing addresses several major objections to the idea of machine intelligence, including the mathematical argument. The argument from consciousness, supposed machine limitations. Lady Lovelace's claim that machines cannot originate anything, that even appeals to extrasensory perception. He responds to each one by showing these arguments either misunderstand what machines do, apply equally to humans, or rely on assumptions not grounded in logic or evidence. Turing maintains that the imitation game remains a robust and fair method for evaluating machine intelligence and predicts that many of these objections will diminish as technology advances. In step 7, titled Learning Machines, Turing shifts focus to how machines might learn rather than be explicitly programmed. He suggests that we should not try to build a fully formed adult mind, but instead create a childlike mind and train it through experience, much like human education. Drawing analogies from natural processes like evolution, he argues that machine learning guided by human input can lead to a...
Hi, I am Trista Makahene. I am a freshman political science major from Fitchburg, Massachusetts, and I'll be discussing John Searle's views in his famous 1980 paper, Minds, Brains, and Programs, where he talks about the relationship between minds, brains, and machines. So John Searle's essay, Minds, Brains, and Programs, it basically challenges the idea that machines can truly understand or have minds just because they run automated programs. John Searle responded directly to the claim that strong AI is categorized as computer programs or AI that can simulate human minds and has the same level of intelligence and understanding as a human being. And a weak AI is more a computer program or AI that can perform specific tasks but lacks true understanding and consciousness. So he responded directly to the claim of strong AI, which argues that a computer running the right program could have a mind and understands things like humans do. But John Searle disagreed with this claim. He introduced a key thought experiment, the Chinese room experiment, to show that following program, even perfectly, does not equal understanding. A person inside a room could manipulate Chinese symbols using a set of instructions without understanding Chinese at all, which is basically what happens in his experiment. Similarly, a computer could process inputs and outputs in a way that mimics understanding, but still lacks consciousness or a genuine comprehension like humans have. So Searle makes a distinction between syntax and semantics to support his argument. He basically just says that computers operate through syntax, meaning they manipulate symbols based on rules or automated programs that they are given, but they don't really understand the meaning, the semantics behind these symbols. So according to Searle, human minds do more than process information. They give it meaning and they understand it because humans also have their own background knowledge that we obtain throughout our life. So therefore, no matter how advanced or human-like a computer program or AI seems to be, it can never truly understand or be conscious like a human brain because it doesn't have the biology or mental states necessary for consciousness. In essence, John Searle basically believed that mental states like understanding, thinking, and consciousness, those three main things, are not things that can arise from running a program or they're not things that computers have or can do. They are tied to the physical and biological nature of human brains, meaning that while machines might simulate human behavior or appear to understand language, Searle says that they are fundamentally different from human minds. Searle's work pushes us to question the limits of artificial intelligence and reminds us that replicating behavior is not the same thing as replicating understanding.
Hi, my name is Kendall Williams. I am a first-year philosophy major from New Orleans, and I will be comparing and critiquing Turing and Searle's arguments on minds, brains, and machines. To compare Turing versus Searle on minds, brains, and machines, Alan Turing asked a new question. Instead of can machines think, he asked can machines act like humans? He created something called the imitation game, where if a computer can talk like a person and fool someone into thinking it's human, then we might say it's intelligent. Turing believed that if a machine acts like it has a mind, that's good enough to say it does. However, John Searle disagreed. He believed that even if a machine acts like it understands something, it doesn't really understand it. It's just following rules and moving symbols around. Searle came up with a Chinese room example. Imagine someone inside a room who doesn't know Chinese but uses the rule book to give correct answers to someone outside in Chinese. From the outside, it looks like they understand, but they don't. Turing thought that what something does is more important than what it's made of. He believed that minds could be built from machines even if they are made of wires and code. In comparison, Searle believed that what something is made of matters. A machine might act like a person, but it doesn't have a mind like a person unless it actually has a brain or something like it that can understand. In short, Turing focused on the behavior of how something acts, whereas Searle focused on consciousness and understanding, which is what's really going on inside. To critique Turing's argument, one big problem with Turing's ideas is that it focuses on not only how things act, but what they feel or understand. Just because a machine acts like it understands doesn't mean it actually does. Searle's Chinese room example shows this well. Just following rules to give correct answers isn't truly understanding something. Turing says if a machine fools us, we should treat it as intelligent, but that forgets certain things like feelings, awareness, and true understanding. His view doesn't explain one's inner experience, which is what it's like to be a person or to really think. He's also assuming that passing a test like the imitation game is enough to prove intelligence, but that is not true. Turing believed that machines would get better and better and eventually think like humans, but he didn't explain how machines would actually have thoughts or feelings, not just fake them. To critique Searle's argument, Searle believes that only biological brains can have thoughts or understanding, but that might be too strict. Let's say, what if something non-biological, like an incredibly advanced computer, could have a mind too? In the Chinese room example, Searle says that a person doesn't understand, but some people argue maybe that the whole system actually does. Searle dismisses this idea quickly, but maybe he shouldn't. His view makes it seem like only brains like ours can think, which might limit how we think about building or studying and other kinds of minds. Also, it's hard to prove that what counts as an real understanding. Searle says computers don't have it, but we can't fully understand how understanding works, even in humans. He also might be ignoring the possibility that real understanding could come from complex machines, especially as they keep getting more advanced. Searle wants to protect the idea of real thinking and feeling, but he might be missing how machines could eventually develop their own kind of mind, different from ours, but still real.
To wrap up this discussion, Alan Turing believes in the idea that machines are able to think in a way similar or comparable to humans, with the belief that the imitation game is a good allegory for how thinking works, believing that if a machine can fool the interrogator into thinking it's a human, then the machine qualifies as thinking. He believes that machines and humans are both capable of thought. Turing attempts to avoid the idea of whether or not machines have minds, or whether their mind exists. He focuses mainly on the idea that both humans and machines can think. On the other hand, John Searle believes that machines aren't thinking. Instead, they're providing syntax without semantics. Syntax is the structure of English, and by claiming machines are only capable of providing syntax without semantics, Searle is basically claiming machines are incapable of understanding what the information they're providing means. The machine is just structured to give the answer after a specific question. Our group agrees with John Searle's claim and disagrees with Turing's. This is because Searle's claim is more logical from an inside perspective. To an outsider who doesn't know how the computer thinks, when you use a search engine or the computer loads, it may look as if the computer is thinking to itself before developing an answer. But the problem lies with what you define thinking as. Our group would determine that thinking involves a level of understanding of the concepts one is thinking about. Searle's Chinese room experiment shows how the process computers go through lacks comprehension or understanding. In the experiment, the person in the room reading the Chinese guidebook and answering the questions has no idea how to actually read Chinese. They're not given any English translation of what the question or their provided answer means. The person isn't thinking up an answer. Instead, they're just using a system to provide them with the answer with no thinking being used in the process. This is the key issue with Turing's argument. If someone asks a student to multiply, the student can't possibly give the right answer if he doesn't know what multiplication is. Any answer that student gives without any understanding wouldn't be a result of him thinking, it would just be a result of him guessing. Additionally, if a friend next to him pulls up the answer or says it out loud, then the student didn't actually think about the answer. He was given the proper answer to the question without any thinking on his part. If a computer is filled with information and told to provide X information after Y input, the computer isn't thinking. It's completing its machinations. It's following its system. Once you acknowledge this glaring contradiction in Turing's argument, it's hard to agree with his claim. As long as thinking requires an understanding or comprehension of what is being thought about, machines will continue to be labeled as things incapable of thinking. Turing's imitation game falls flat when you acknowledge that a computer can only trick the interrogator from an outside perspective. If you were to look in at the computer and see that the system is set up to say X answer after Y input, then you'd know right away the computer didn't think about its process at all. It already knew what to say without having an understanding of what it's talking about. And you can't really define that as thinking. That's why our group agrees with John Searle's claim.